On a clear, dark night, we can all marvel at a crystal sky brimming with stars. And beyond what we can see with the naked eye, powerful telescopes confirm an expansive cosmos chock full of galaxies and stars and swirling clouds of gas and dust and planets and comets and asteroids. But here is the amazing realization. Tallying the mass and energy of everything in the cosmos that we can see accounts for less than 5% of what there is. The rest, more than 95%, is invisible to even the most powerful telescope imaginable because it is all dark. The dominant ingredients in the makeup of the cosmos do not emit or reflect light, and so have been named dark matter and dark energy. But if we can't see the dark side of the cosmos, how do we know it exists? Well, scientists have deduced the dark universe indirectly by its effect on the universe that we can see. And among the scientists who were the earliest champions of a cosmic dark side was James Peebles, one of the most influential cosmologists of our time. Peebles has played a critical role in numerous cosmological advances, including the discovery and decoding of the cosmic microwave background radiation, a decisive tool for analyzing the dark universe and refining cosmological theory, contributions that earned Peebles the 2019 Nobel Prize in Physics. Welcome, Jim. Thank you so much for being here. So many people who go into science or mathematics often tell stories that they knew from when they were like 4 or 5 years old, that this is what they wanted to do. But I gather for you, the journey was a little bit more circuitous than that.
True. I think as a student in high school, I was unsatisfactory, not because I was at all rebellious, but because I was a dreamer. I didn't pay much attention to the courses. I passed them, but I didn't participate in any sports activities, communal activities. I was a dreamer.
And was that like by yourself dreaming?
Yes, largely by myself.
In books or?
Well, you know, my father was handy with his hands and he liked to build things. I like to build things. I like to mess around with electric motors, transistors, transformers. Because I was not paying attention, I went into engineering, which I did because I knew engineers built things and I knew I built things, so that seemed right.
I mean, you say you were not paying attention, meaning?
I didn't ask anyone. I just entered the University of Manitoba.
Okay.
Where I discovered at the engineering department that what I really liked were those courses in physics. So I transferred, and it was the best thing I could have done.
Right. And was there a particular course in physics that really made it clear that that's what you wanted to do?
More important, I think, one professor, which is what you need, who took an interest in me, taught a good course that taught me a lot about physics. And then he declared, he had been a graduate student in physics at Princeton 10 years earlier, and he decided, you should go to Princeton. So, all right, Ken. I went. And it was wonderful. Of course, it was a big fish in a small pond becoming a little fish in a very big pond. But I survived.
Yeah. And I gather at that time at Princeton, you had two really iconic individuals who were starting to think about gravity, but in very different ways. John Wheeler is the one who, we in the theoretical community know well, but of course Bob Dickey was there as well. Can you give a sense of their different approaches?
Well, you summarized it well. To John A. Wheeler, Johnny, general relativity was such a beautiful theory that it was almost certainly a good approximation to reality. Bob Dickey certainly understood theory well, but he was a brilliant experimentalist. he had spent 10 years after arriving at Princeton doing laboratory, what you might call quantum optics. He decided that gravity, experimental gravity, had languished since the 30s when difficult experiments were done, but with technology that was so much more crude than what could be done with the electronics that came out of the Second World War. So Bob decided to set up a program of tests of gravity physics, including the old classics, but do them better with modern electronics.
And like Oudtvo's experiment?
For example, yes. Many others, testing active and gravitational mass equivalence.
Yeah.
Very clever experiments. So I am a theorist, but his work was much to my taste. So I started with him. He is the one who said, you might consider looking into the expanding universe theory. I did.
And where do you think that came from Dickie? Was he just starting to think about cosmology and applying general relativity? Was it in the air?
Not in the air. Although Bob and John were quite close and familiar, they had very different worldviews. John, well, Einstein's general theory of relativity is so elegant. To Bob, it's a theory, and you don't trust theories until they've been tested. And so he was looking for tests, all kinds. He had quite a large group of graduate students doing lots of very interesting experiments. And of course, gravity figures large in the theory of the expanding universe.
Yeah.
So he became interested in it. That's why he suggested I start working in it.
And did he have a specific idea, I gather?
Yes, he did. Yep. He decided that, well, of course, you have that old problem. What was the universe doing before it was expanding?
Yeah.
One idea that people had discussed is it was a bounce. The universe collapsed, bounced.
I guess Tolman was pushing that.
Tolman was pushing that. It's a naturalist notion.
Yeah.
Bob noticed and worked out the elegant physics of that in a collapse, it's going to be thermodynamically irreversible. We're going to produce a lot of entropy, which would be largely in radiation. So this universe that's now expanding would be expected to contain a sea of radiation. That radiation would be expected to have a specific spectrum, that is to say, the intensity at each wavelength. He had invented during the war a microwave radiometer, a device capable of very sensitive measurements of radiation. He suggested to two of his young people in his group, David Wilkinson and Peter Roll, why don't you build a radiometer to see if there's anything there? And he said to me, so casual a remark, why don't you think about the consequences of this experiment, whether a detection or non-detection?
Right. Now, a non-detection would have been interesting.
Oh,
too,
yes.
right?
Oh, yes. And of course, it has implications. You have a real challenge if the universe in the very early stages of expansion were cold.
Yeah.
Because the protons would fuse to make heavy elements. And that's not the way our universe is made. Most of the baryons are already hydrogen and helium. So, of course, there's a way out. You postulate degenerate neutrinos,
Neutrinos, yeah.
And so that's a possibility to consider. I, of course, worked on that. But it turns out the radiation is there. And it has been wonderfully instructive.
Now, the discovery of the radiation is itself an interesting sociological / physics story.
Oh, yes.
Together.
Oh, yes. You know, it goes a long way back. Already in the early 1940s, people observed interstellar atoms and molecules by the absorption of light from stars behind them. The molecules cause absorption line, the atoms cause absorption lines. The discovery was that the molecule cyanogen, carbon and nitrogen stuck together, is observed in interstellar gas in absorption. And startlingly, it's observed in absorption at the first excited level. Remember, in quantum physics, energies are quantized in an isolated system. It was a puzzle. Why should the cyanogen in interstellar space be in an excited level?
Right.
One possibility, slightly mentioned, maybe there's a sea of thermal radiation that's pushing it up to the first excited level. Then again, when people started at Bell Laboratories in northern New Jersey, started thinking about communications by microwaves, which had, to me, the rather unhappy consequence of producing those cell phones that I see our students at Princeton University walking around staring at rather than admiring that beautiful campus. But
among other detrimental effects.
Among
yes.
others. 1959, engineers at Bell Labs developed very sensitive detectors to use in communications. They found that receivers were receiving a little more noise, a little more electromagnetic radiation than they could account for that for. That was a dirty little secret at Bell Telephone Laboratories in northern New Jersey.
And this is before Penzias and Wilson.
Oh, yes.
Right? Yeah.
Right. 5 years before. It remained a dirty little secret until Penzias and Wilson, two young people from physics, 1964, decided, well, we ought to find out the source of this radiation. They worked they're to be credited for refusing to give up the search for the source of this radiation. And, you know, I'm impressed that their bosses allowed them to keep going. This in a commercial research laboratory. But one, you know, Bell Labs at that time they had a monopoly on the telephone. They were controlled, and so they couldn't charge too much money, but they had a lot of money, a lot of revenue.
Yeah.
And they spent
that resulted
it wisely.
in freedom, right?
Oh, boy.
Yeah.
Transistors. It was just a very impressive place. Anyway, they allowed these guys to keep going. Penzias and Wilson also did something very sensible. They complained. Why can't we find... The complaints actually eventually reached Princeton, where Bob Dickey had, as I said, suggested the two of his young members of his group build a radiometer of the kind that Bob had invented during the war to look for this radiation. So the two met, and the recognition, wow, maybe that noise in microwave radiation came from the early universe.
Now, often the story is told that the next step was a telephone call.
Yes. So we were having lunch in Bob's office, bag lunch. Phone rang. Bob answered. I could see David Wilkinson's ears pop up. Mention of, sources, radiation leakage through the antennae, through the joints of the microwave, microwave channels, and it was pretty clear. And then Bob turned and said, "Well, we've been scooped." You know, I'm often asked, what was our emotional reaction to that?
Yeah.
And
what was your emotional reaction to that?
You have to bear in mind, this experiment was a blind search in the dark. No guarantee that anything would be detected. Of course, it was not detected. That's interesting, but still. The fact that Bell had shown that there is something there to be further studied experimentally and to study theoretically, that's my job, to find its implications, was very exciting. So it's often said, well, you must have been chagrined, but certainly not me. That was a real exciting moment.
How about the more experimentally oriented members of the group?
Well, they had something wonderful to do. So David Wilkinson spent the entire rest of his career.
Yeah.
And I spent the entire rest of my career just following Bob's suggestion.
Now, you and Penzias and Wilson, the two groups, I gather, agreed to write two separate papers.
Right.
One on the experimental discovery of the microwave background radiation and one more on the explanation and prediction from a cosmological perspective.
Right. Followed The first being the detection, the second, the implications.
Now, when you look at the experimental paper, I've always been taken by the fact that there's zero mention of anything but the experimental detection, not even a word about cosmology. Was that by agreement, or did Penzias and Wilson just want to state the facts and not muddy it with any potential theoretical interpretation?
That's probably a good motivation, but I don't know. I never discussed it with... In fact, Bob Dickey directed the papers. I don't know whether he suggested or whether Penzias and Wilson realized. Well, you made a very good point. Let's not muddy the water.
Right, right. Now, of course, history shows that the Nobel Prize was awarded for this discovery to Penzias and Wilson. Some have suggested that there could have been a more generous spreading out of the prize, perhaps to Bob, So what's your view of that?
Well, I was totally disgusted. I deeply respect the Nobel Prize and the Nobel Committee. Those people work really hard to get it right. They work really hard. But this is a brainless move. It should be Penzias, Wilson, Dickey. Dickey invented the instrument. He suggested the use, and he told the Bell people what they may have found. Yeah. It was obvious.
How did he take that? Did he show any sense of?
Well, I remember he was a little chagrined. A little chagrined. You should understand, the people at the Nobel Committee work really hard.
Yeah.
But they're people. They make mistakes.
Right, right. Now, the other interesting part of the story is that in time, you and others recognize that there had been even earlier intimations of these ideas from
right.
Gamow and Alpher. Can you just give us a sense of that backstory?
Well, so Gamow had the deepest physical intuition of anyone I've ever encountered, just dazzling. Maybe it's inevitable that such brilliant intuition must go along with a certain dislike of authority. So Gamow, during the 30s, he was one of the leading authorities in nuclear physics. At the time, shortly after the World War II, that is relevant, he was finishing the third edition of his book on nuclear physics. Why wasn't he part of the effort at Los Alamos to develop the atomic bomb? Everyone else was there. It was his refusal to take seriously the notion of security.
Yeah.
So a brilliant character. In 1948, he wrote a paper with Ralph Elfer, and since Elfer and Gamow look like the second and third letters of the Greek alphabet, he put in by hand the name of Hans Bethe to write a paper famously known Alpha Beta Gamma. The paper assumed a cold start to the expanding universe. It's totally wrong.
Right.
Later in that same year, his intuition hit upon what was totally right, the notion of a hot universe, with many of the physical considerations that were then fleshed out by centuries, by many people. It's so funny that in the first of the papers where he got it right, A Hot Big Bang, he mentioned the Alpha Beta Gamma paper and saying, due to a numerical error. But it wasn't a numerical error. This is Gamow.
Right.
I don't care about that old paper. Anyway, Gamow got many of the ideas right. But because he was such a flighty person, and because shortly after two brilliant papers in 1948, he streamlined the idea down to a theory that was just not logical. So his theory dropped out of sight.
Yeah.
It wasn't forgotten by everybody, but I, a physicist, knew nothing about this. So I had to start from scratch. Gamow's theory didn't make its way into the textbooks.
Yeah.
In particular, the wonderful series of theoretical physics by
Landau and Lifshitz.
Landau Lifshitz.
Yeah.
They had a third of their book on classical theory of fields is general relativity theory. Ironic, because it was not a theory that was at all well tested. It included the notion of the expanding universe, but they introduced a footnote. This may be all wrong because the universe may not be homogeneous.
Right.
They didn't mention the hot Big Bang. They didn't mention Gamow. And so I didn't know about Gamow.
Sure.
So that was eventually, the connection was made. By the time of those two papers you mentioned, our paper has references. Though I have to admit, among those references was alpha, beta, gamma. I hadn't done the homework to recognize that that paper is wrong. I let it get in there.
Yeah. But there's also an Ralph Alpher paper with Hermann on the CMB and predicting, I guess, a 5-degree background temperature.
Right. That was their great contribution.
Yeah.
Following Gamow's two papers in 1948, they pointed out that in this theory, you would expect that the universe is filled with a near uniform sea of radiation at a very well-determined temperature, around 5 degrees or maybe 8 degrees, or close enough to be consistent with what was later discovered.
Yeah.
Incidentally, I mentioned the cyanogen temperature. It was 2.3 kelvins. Alpher, 5 kelvins. The observations, 2.3275.
Right.
Wow.
No, it's amazing.
Yeah.
And so we now had evidence that this thermal background is there, which is giving us evidence of the hot Big Bang approach to cosmology. But as you said, you didn't stop there. This is really the beginning, because now that you have this relic from the Big Bang, you can start to push further. So what was the next step in trying to understand this radiation, what it means?
The very first next step, the key step, is does this radiation really have a thermal spectrum? That is to say, you give me one parameter, a temperature, I'll tell you the intensity at each wavelength.
Yeah.
Attempts to check that were very difficult because you had to get above the atmosphere to reach the peak of the radiation. And getting above the atmosphere and doing experiments is really difficult.
Yeah.
The result was that during the 70s, there was a persistent indication of an anomaly that the spectrum isn't quite thermal. That was that really made me uneasy, because it's easy to imagine that the early universe was energetically mixed up enough to produce radiation enough to have disturbed the spectrum. If it did that, then the distribution of radiation across the sky is giving you a measure of some complex process.
Yeah.
That was a horrible thought. It wasn't until the early 80s when John Mather and others flew the definite experiments that showed, wow, it's almost exactly thermal. That meant that the small departures from an exactly uniform thermal sea was telling you about the nature of departures from uniformity in the matter distribution. Suddenly, you had the prospect of a precision test, compute the evolution of the mass distribution, predict its present properties, and then measure them. And that was really key, because you could make these computations very reliably. They're just linear perturbation theory. And that means, because you can also make precision measurements, that you had a wonderfully tight test of theory against observation.
Which is very new in a realm of cosmology,
it made a convincing case that we're on the right track.
Right. And so just to review that key idea, you're saying that small inhomogeneities in the matter distribution, they would be centers around which additional mass and a kind of snowball gravitational effect would accumulate, giving rise to galaxies. So this is essential to understanding how these structures exist.
The word snowball is a hazardous point. Galaxies are complex.
Yeah.
And so their properties aren't really a very good test of the expanding universe. It's the slight departures from uniformity in the radiation
Right.
and in the large-scale distribution of the galaxies that you can compute reliably and you can measure pretty reliably. And my goodness, they agree.
And in fact, there's a beautiful graph which
There
shows
certainly is.
the anisotropies in the microwave background radiation against the measurements. Well, here's this is the black body curve.
This is what made me feel good. Early 1980s, that's John Mather. Is there a second one that
There should be.
shows? Interesting that there were many attempts to measure the intensity of this radiation as a function of wavelength. Two people drove experiments that got it right. John Mather's experiment was proposed to NASA 15 years before the measurement. Beautiful work required an enormous effort to make that measurement. In the year John Mather submitted a proposal to NASA, Herb Gush, lead author in this measurement, flew a rocket. Herb Gush is a Canadian, University of British Columbia, more modest funding at the time in Canada. He couldn't fly a rocket that was adequate to carry the shielding that was needed, but he flew it anyway. He made the first attempt at the measurement of the spectrum from outer space. 15 years later, and many failed attempts. Shall I mention an example of the horrors of rocket measurements?
Why not?
Solid fuel rocket. It carries up the rocket, the instrument. The explosive bolts release the instrument. It goes ahead and leaves the rocket behind. But some of the solid fuel in the rocket didn't burn, caught fire after the instrument package had been released, and the rocket ran ahead of the instrument package and sprayed it with noxious chemicals. Oh, gosh.
It's a tough life.
You have to be tough.
Yeah.
Eventually, though, within months, the two got the measurement. Both would have made the case that it's thermal radiation. John Mather received the Nobel Prize for that measurement. Well deserved, well deserved.
Yeah.
Herb Gush got the deep respect of his colleagues, but nothing more.
So is that another example of the Nobel Committee trying their best, but perhaps not getting
Yes,
it?
thank you.
Yeah.
I'm from Canada, and so a certain chauvinism
Yeah.
maybe is apparent here.
So this is the curve that establishes the black body spectrum that any of you viewers here or in digital, you take a basic physics class in statistical mechanics, thermodynamics, you learn about this curve. A box at thermal equilibrium will have this particular spectrum.
Right.
And then, amazingly, the deviation from perfect thermal spectrum was the next major result that allowed one to really, as you say, do precision tests.
And you understand it was the absence of serious deviations which would have meant serious deviations from linearity in the early universe would have made the whole thing very impossible.
Right.
But there it is. You can be quite sure the early universe was quite tranquil, slightly disturbed by growing departures from homogeneity.
Now, to take this to the next step, you introduced into cosmology another idea which has been with us ever since, dark matter, in particular cold dark matter. So can you explain the trajectory in your thinking that leads to that step?
The galaxy distribution is quite clumpy. That's fine. Gravity would naturally draw things together and make a clumpy distribution out of something that was almost exactly smooth. But to move around the matter to make it that clumpy would seriously disturb the microwave radiation. So how do I understand that the microwave radiation is so very smooth while the matter is so clumpy? The way out had to be an ad hoc guess that most of the matter in our universe is not made of the baryons, electrons, protons, neutrons of the standard theory, but rather something invented ad hoc, dark matter. let it be cold to begin with, because that's simple. It's the first thing to try.
And also it keeps the pressure low, presumably.
That's right. So it's easier to compute.
Yeah.
And ask yourself the question, would this scenario work? The idea is simply that as gravity is drawing matter together, baryonic matter together, it will pull in radiation. But if most of the matter is not baryonic and does not interact with the radiation, then it won't disturb the radiation very much. So already in 1982, I had computed the quadrupole moment. I had a prediction. It's sort of fun to realize how long it took to check that prediction, but a couple of decades.
Yeah.
But it was found. Then, of course, we get to this. The baryonic matter and the radiation in the early universe strongly interact because the temperature is high enough to strip atoms of their electrons. The electrons scatter off the radiation strongly enough to tightly couple them. The electrons scatter off the ions strongly enough to couple them. So ions, electrons, and radiation act as a fluid, which has a pressure, which means if it's disturbed from uniformity, it will oscillate like a wave. That oscillation like a wave means that the final mass distribution and the final distribution of the radiation are computable if the departures from uniformity are small, so you can use linear theory. And here are dazzling results recently obtained. The wiggles. You understand, of course, resonance, which is a key thing. If I had a bottle, I would blow across its top and I would make a tone, which is set by the boundary conditions in the bottle. The universe has boundary conditions. It must start smooth, and it must end this coupling when the radiation falls to a temperature of about 1,000 Kelvin, when the electrons can combine with the ions, and that lets the radiation free to move and the matter free to move. So you can compute all that. In this graph, the wiggles are the results of that resonance, lucky and unlucky modes that grow and modes that diminish, that can be computed. The solid curve assumes particular values for parameters, such as the mass density in dark matter, the mass density in baryonic matter, the abundance of helium, which matters. And the solid curves are adjusted to fit those constraints. The data points are data points. They're not at all well measured in the radiation at the very small L value, and L is like a wave number. It's a reciprocal of a length. So that's large length scales where we don't have a very good sample of the universe because you can only see so much of it. The rest, spectacular agreement. And even more spectacular to me, the distribution of galaxies on large scales is measured in a very different way. So you have different theories matching data obtained in very different ways and getting a consistent story. It's really dazzling.
Shockingly dazzling that a calculation that really can be done on paper and pencil, can yield something so precise about the nature of the universe at large.
Nature seems to operate that way.
Yeah.
And it gives us very important point. You don't trust a theory until you've had it tested. And what you just saw is a really demanding test that it convincingly establishes the hot Big Bang, general relativity theory, as a remarkably good approximation to reality.
Now, there was another anomaly that you were paying more attention to than most at this time regarding the expansion rate of space.
Yes.
In fact, I've read in various places that people would find it irritating when you'd bring up this issue at times. But it turned out, again, to be right. So maybe give us some insight on what that was all about.
Right. So Einstein another spectacularly intuitive person and maybe better self-controlled than Gamow. Einstein decided first he introduced his general theory of relativity in 1915. It was a spectacular intuition, so beautiful that many people accepted it, but it was not based on much empirical evidence.
Right.
On the other hand, so then 2 years later, he decided, well, I'm going to try to apply this theory to the structure of the universe. For reasons that no one has ever explained to me, he decided that the universe is uniform in the large-scale average. Why did he assume that?
Simplicity?
Simplicity. He found that this universe would not stay static. Of course, it's obvious that the universe is static. It's not changing. Of course, it is changing. But to keep the universe from collapsing under gravity, he introduced a term he added to his field equations of general relativity. So it earned the name the cosmological constant. That added term, Einstein later emphasized, was added only because he had to fit the observations. He did not realize there was an observation that the universe is expanding. As soon as he learned that, he decided the cosmological constant must go. But now in the 1990s, the early 1990s, it was becoming very clear that if you didn't put the cosmological constant into Einstein's field equations, then the motions of the galaxies indicated a mass density that is quite large, small compared to what you would expect from the rate of expansion. At the time, people were so impressed by the simplicity of Einstein's field equation and of a near homogeneous universe, and so impressed, I think, by the two facts that the cosmological constant is disliked by Einstein, and because if you accept standard quantum physics, then the zero-point energy of the electromagnetic field would add up to an absurdly large cosmological constant. The only solution, something caused the cosmological constant not to be there. That was very convincingly convinced many people. Surely there is not a cosmological constant. But I was doing studies of how the galaxies are distributed, how they're moving, and to make that story fit, I had to assume a mass density considerably less than was required by this universe without the cosmological constant. So I proposed adding the cosmological constant. That did offend people.
Yeah.
I remember one young person, very capable now, a great scientist, saying, "You're only doing this to annoy." And do you know the old Lewis Carroll, be to your little boy, whenever he sneezes, he only does it to annoy because it knows it teases. And I must admit that I kind of enjoyed going to conferences in the 1990s and pointing out the evidence for the cosmological constant because I knew it teased.
Right. And just from the physics standpoint, the cosmological constant with the right sign would yield an outward push.
That's exactly right.
That would assist the expansion.
That would solve the problem.
Right.
So now in that image you saw of the oscillating from the computation, it has a cosmological constant that, it's needed.
And what size were you suggesting back then? Were you giving a numerical?
Oh, I was, but I don't remember these things. Instead, it's a dimensionless measure. What is the ratio to the baryonic density? And I don't even remember that number.
Was it like 0.7-ish? Or
is that a hint? I adjusted it to fit the measurements, which were only, the mass density is the essential point, and it was, I think, reliably nailed down to a factor of 2.
Right.
So it was.
And then the beautiful thing is 1998, when the observations from the distant exploding supernova gave an answer that showed there was a cosmological
that
constant.
produced the Nobel Prize.
Yeah.
Just a magnificent result that people had been trying to achieve ever since the 30s. people knew it would be a critical measurement.
Yeah.
But if we'd had only that, it would have been unsatisfactory. How do you know that supernovae at redshift 1 are really very similar to...
Yep.
At the year 2000, plus or minus 1, the first detections of these oscillations were found to require a cosmological constant.
So you found that more convincing?
Yes.
Really?
Because it's simpler. Simple to compute. And whereas the evolution of supernovae is impossible to compute.
Right.
So I was not convinced by the supernovae. I deeply admired it. Those people did a great thing.
Yeah.
But as a practical matter, it was the radiation that whose anisotropy was detected that convinced me.
Now, does it bother you, or maybe that's the wrong way of framing it, does it make you wonder about the fact that these dark entities, the dark matter, the dark energy, they're kind of patches?
Yes, they are.
In order to make things work. They're not something that we've directly detected.
That's right. They're patches.
And where do you come down on that? Do you view them as sort of a temporary fix?
I hope so.
Or are they the answer that ultimately will be directly confirmed?
I can't believe they're more than a temporary fix. Got to be more interesting. Has to be. A wonderful challenge for the next generations. Learn how to make a more realistic model for the nature of matter in the universe, dark and light.
And so the failure to detect dark matter over many decades now,
yes.
Where does that leave you on thinking? We just have been looking the wrong way, or it's a more exotic species?
Nobody ever guaranteed that we could make any sense of the universe around us. And I've often wondered, why were people so sure that the universe operates in a rational way? You see early examples of it. Tycho Brahe, 2,000 years ago, had a theory for the motions of the planets. It was an ad hoc theory, circles, but yet he managed to get very good predictions.
Yeah.
And I guess he wasn't particularly worried about the fact that, well, why are circles so very... You do what you can.
Yeah.
So far, we have not found any flaw in the use of dark matter and dark energy, cosmological constant, and so we'll stick with it. But we certainly lust after hints of failure of the standard theory that will hint to a still better theory, because it will have more interesting properties for the dark sector.
Would you be surprised if, say, 30, 50 years from now, the dark sector has been replaced by some new theoretical idea, some new force of nature, something of that sort?
Right. I certainly don't expect that the main outlines of the standard theory we have now are wrong.
Yeah.
But in detail, I think they've got to be wrong. And who knows, maybe tomorrow you'll hear news of detection, or maybe you will never know. Never a guarantee that we can solve all the problems that are posed to us.
Yeah, for sure. So in terms of anomalies with the standard theory, there are a variety of hints of things to come.
Right.
One of which is the so-called Hubble tension.
Yes.
When you measure the expansion rate of the universe, basically in two different domains, early universe, later universe, and try to extrapolate, they don't quite meet.
Yes.
Do you think that's a big clue?
Number one, I'm impressed that they almost meet, because you're comparing what happens in the universe recently and in the remote past. That they should agree at all is startling to me. But of course, they don't agree. That may be because of systematic errors. It would have to be, I think, in the local universe measurements. Systematic errors may be the culprit, or maybe, and it's what I'm hoping for, this is a true anomaly, which is telling us there's something observably wrong with the standard theory, so let's look for what it is. And of course, let's also look for more anomalies. And maybe if we have enough, we'll see how they all fit together.
You think James Webb Space Telescope observations are going to resolve this particular anomaly?
Only know if you try.
Yeah. Right. So it's still very much up in the air, but one can hope as we go forward.
And it's good to be looking in lots of directions, by lots of ways.
Yeah. Now, as we've gone forward to refine cosmological theory, scientists, you, the community at large, have taken on problems which in an earlier age were viewed as, we'll get to that at some point, but we're not ready to yet. And among those, for instance, are questions that inflationary cosmology has tried to address. This idea that in the early universe, there was some phase of rapid expansion driven presumably by some energy that mimicked a cosmological constant of a very large value in the early universe and drove everything outward. There's controversy now about inflation, although I think some of the inflationary proponents may get angry at me for calling it a controversy, but there are differing opinions right now on the inflationary structure. Where do you come down on this?
I have to respect these beautiful theoretical ideas. After all, Einstein's general theory of relativity, based on almost pure thought, was wonderfully successful. I got to respect that. And I've got to respect the possibility that inflation is in the same line. But I don't trust it until we have some evidence. And unfortunately, it's very difficult to get empirical checks so that early on. So I say, yes, let 1,000 ideas bloom. And meanwhile, wait and hope we can think of something that can test these ideas.
Now one of the particular issues, there are a number, but some people bristle at a fairly generic quality of inflationary models, which is they make our universe not the only universe.
Yes.
So the inflationary fuel that drives the rapid expansion, it's not exhausted by the expansion in our realm, and the leftover fuel, roughly speaking, gives rise to other big bangs in other realms. Now, for someone like you who wants things to be tested, which of course is the way science is meant to progress, does the idea of other universes seem nutty to you? Or are you willing to sort of allow for a tested theory to make untestable predictions?
It should be done. But how seriously should we take the ideas?
Yeah.
I'm quite comfortable to hear about the multiverse. But I might mention one point.
Yeah.
We talk about eternal inflation. But eternal inflation is very clear, can be eternal into the future, but it can't be eternal back in the past.
Yeah.
We run into these logical problems as well as empirical problems. And we pay attention to them.
And do you think we'll ever be able to deal with the issue of the past? I mean, the question that I'm asked most frequently, both by students and by the general public, is, okay, you've got this Big Bang idea, okay, maybe inflation, but what got it started, right?
Yes.
Why was there the inflaton field? You know, why was there any expansion in the beginning at all?
We're waiting out of our subjects.
You think so?
Yes.
And which subject are we wading into?
Speculation. Many possible ideas.
But you think that it will resist scientific explanation? Do you think that there are questions of that sort that will simply be beyond the reach of the methods of science?
I dislike definite statements.
Yeah.
So I say it certainly looks likely that we will not be able to answer all questions.
And how do you feel about that?
Well,
is that just the way it is, or
no one told us we could find answers to all questions.
Yeah.
I'm amazed at how well we've done.
Yeah.
And I'm sure we'll be doing even better. There's a great future ahead of you all in physics. It's a good subject, but you're not going to get all answers. That's just, to me, obvious.
So the big one that Leibniz asked a long time ago, why is there something rather than nothing, that is among those, presumably?
I don't lose sleep over that question.
Right. So as we turn to the future, there are a number of missions that are planned. We've made reference already to, obviously, the discovery of the microwave background radiation, then the confirmation of the black body spectrum with COBE, and also the Canadian experiment that you described, the anisotropies that came from COBE, and then we got a lot more information from WMAP and from Planck. We have James Webb up there now
Yes.
doing remarkable work. What of the upcoming missions are you excited about?
Well, we've reached a point in this subject where there are two lines of investigation. First, you can do measurements that have already been done much better, and you should do that better. You perhaps will find that what looked like close agreement of theory and experiment isn't so close. Maybe there's an anomaly. That's very important to be done. But you know, in the rush to advance the science, you do tend to leave behind little oddities that you feel, well, we'll get to that later.
Yeah.
And we don't. There are, in cosmology, many questions that remain open that are a little outside the general line of approach of the big experiments. To do a big experiment, you've got to be pretty sure that you know the answer. And to find big missing pieces of the puzzle, you have to step back and start thinking and maybe do a small experiment. I harbor the hope, and I'm working on it, that there are puzzles that were left behind in the rush to advance that are pointing us to issues that are going to teach us how to do better in cosmology.
Do you have any that you can share with us as some final words in our conversation here of where you're putting your attention at the moment?
Do we have a photograph of a galaxy?
Do we have a photograph of a galaxy? Imagine that there is one, because we will make it look that way in the digital version of the program.
Okay, a beautiful one is named Messier 101. Nearby, face-on spiral. Wonderful. It's a gorgeous image. Do you see the blue patches? That's where groups of stars have formed relatively recently. Among the groups of stars, there are some that are much more massive than the sun. They are far more luminous. They're hot blue. That's what makes the blue patches. You notice red patches? That's where these massive stars have produced enough ionizing radiation that they've produced patches of plasma. In the plasma, the dominant ion is hydrogen. Its recombination line is a big fat line in the red. Notice a glow of yellow toward the center. That glow extends across that whole galaxy. It is the light of stars similar in mass to the sun. Astronomers have shown that in our patch of our galaxy, there are at least as many planets around stars as there are stars. This is showing us a system that we can never reach. It's 10 million light years away, in which there are some 10 to the 9th planets on which all sorts of things, of wonderful things are happening that we, the human race, will never see. That's one cautionary remark I like to explain. The other is the fantastic spiral galaxy. The evidence is, from observations of other galaxies, that this galaxy is thin, like a discus, all the way to the center. That thin discus is not obtained in numerical simulations of the formations of galaxies within the parameters of the standard hot Big Bang cosmology. It's a real deep puzzle. Why is this thing so thin? And why do the spiral arms go all the way to the center? And I might point to the enlargement on the left from the Hubble Space Telescope instrument. You see how the spiral arms extend almost to the center where there's a bright spot. That's a million solar masses of stars. That's a big number, but trivial compared to the mass of this galaxy. 10 to the 10.5 in stars. In our galaxy, there's a massive black hole in the center. Is there a massive black hole in the center of this galaxy? I'm really hoping JWST turns its power to that little spot and determines whether or not the galaxy stars are moving in such a way as to indicate the presence of a black hole in the very center. We don't know where black holes come from. That's one big puzzle.
Yeah.
The other is we don't understand why the mass around the black hole is so darned close to smooth and moving so slowly that it can form a spiral arm. A beautiful set of puzzles right here before our very eyes.
And do you anticipate insight on that from numerical computational studies that are more refined in understanding the dynamics?
They've been working on it for years and very refined, and so far no one has found a galaxy, to my way of thinking, that matches the properties of this one. That means there's something we've left out of the computation, my bet is. What is it? What did we leave out? Well, no, it's up to you. You need to discover what we left out of this theory.
Great challenge for all of you. One final question before we end here. One recent result from the James Webb Space Telescope is that early galaxies seem to not conform to what we would have thought from the standard cosmological scenario. They're brighter at earlier times.
And more massive.
And more massive. What do you think about that?
Well, it's another example of the fact that we don't really understand well how galaxies form.
And so that...
Another valuable clue.
But do you have any...
Nope.
No guesses of where that's going to go. Again, another challenge for all of you, both live and digitally, who are watching this. It's been a fascinating conversation. Jim, thank you so much for joining us. Please join me in thanking Professor Jim Peebles.